Welcome everyone to lesson 3.2 of Precalc, which is all about sine, cosine, and tangent. Those might sound a little bit familiar. Let's dive on in. Before we even start talking about sine, cosine, or tangent, let's start to talk about angles. And we're going to change how we've fundamentally thought of angles from, prior years, especially like geometry in middle school, to having a very formal set definition. That way we can expand upon that definition and we can build things from it. So this is old news. An angle is formed from two rays that share an endpoint. So they start at the same point and then go off to somewhere forever, usually different places. But if they go to the same place, then the angle would be 0, right? The initial ray is where we're starting our measurement from. And the terminal ray is what we're measuring to. So if I look at this angle here, for example, and I'm going from here to here, this would be the initial ray, and this would be the terminal ray because I'm starting my measurement here and ending here. If I switch them, it kind of switches where I'm going from there. We always describe angles in standard position for us. Almost always, almost exclusively, we're going to talk about standard position. And what standard position means is that when we talk about an angle that's on our xy plane, that the shared endpoint is the origin, and the initial ray falls along the positive x-axis. So if I look here, this is a standard position 45-degree angle. You can see the endpoint here is at 0, 0, and we're starting at the positive x-axis and going up 45 degrees to this terminal ray. So that would be a standard position 45-degree angle. Positive and negative angles. Well, positive, as you can kind of see here, we're going counterclockwise from the x-axis. So if we go clockwise, it would be negative. So a little bit weird to think about. Counter is positive and regular is negative. But if you're struggling with that, think about the quadrants. You've been drilled into your mind with what the quadrants are and their names probably for years now. And our quadrants go 1, 2, 3, 4 in a counterclockwise motion. So we're following along our quadrants. So that can definitely help there. The next big idea we're going to talk about is we really aren't going to use degrees unless we're dealing with an application that specifies degrees. Like if we're talking about triangles, yeah, we're going to use degrees for the most part. But otherwise, we're going to be talking about radians. And hopefully you've been introduced to this concept of radians in probably both your geometry and your algebra 2 classes. So what is a radian? A radian is a different way of measuring angles. And what it is it's the ratio of an arc. So an arc is like part of a circumference of a circle. It's the ratio of the arc to the radius of a circle. So 1 radian occurs when the radius is equal to the arc length, which is a little bit weird. Think about how many radians that might make a whole circle. We'll get to it soon, but just an interesting thought. So let's use our definition of a radian to answer some questions. And I don't know why there's such a big space there. Let's move that one up. Perfect. So if a circle has a radius of 4, so r equals 4, and the length of its minor arc, very complicated way of saying that the part of the circumference we're dealing with is 8.796. What's the measure of the central angle? What's the measure of the angle? Well, the angle is equal to the arc length, which is 8.796, Mr. Whaley, over 4. And that one, complicated. That's not a question you're going to randomly be asked on a non-calculator part of an assessment. So if we quickly do that in a calculator, we get that the angle in radians is 2.199. So, not bad. What if we are given the arc central angle in radians and its radius? How can we find the arc length? Well, arc length is equal to the radius times the angle. And that's the formula I have memorized. And I can manipulate this to find any one that I want. So if I plug in all of my information to this, I get S is equal to, the radius is 2.7, and we have 1.4 pi radians. And we can multiply those two things together. So 2.7 times 1.4, and I get 3.78 pi radians. Now, if you notice, not radians, that would be the length. We don't have a unit for that, so whatever the units are. And since it's length, it would just be regular units, not like units squared or anything like that. So you might have also noticed that we don't really have a unit with our angle. We don't put like a degree mark or anything like that. Radians don't have units, which is part of the reason why they're so useful, is that when you apply them to things, you don't have to worry about canceling the units out or anything like that. And also we're going to end up with pi a lot. Just leave pi there, especially if we're not trying to figure out like on what day did this. If you're not dealing with an application that like specifically needs like a decimal approximated answer, leave the pi. It's so much nicer. It's so prettier. It's so much more pretty. Leave it like that. Last but not least is we have an arc with a central angle of 0.625 pi radians and has a length of 3.125 pi. What's its radius? Well, if arc length is equal to the radius times the angle, the central angle, then the radius is equal to the arc length divided by the angle. So the arc length was 3.125 pi, and the central angle was 0.625 pi. If we divide those two things, we should find the radius, and cool thing is even if you're using a calculator, the pi's cancel. So nice. 3.125 divided by 0.625 is 5. So the radius is 5. Now again, if we had like an arc length of 3.125 pi inches, then you would put inches, but since we don't have a unit, it's okay to leave it without. That is essentially what radians are. Great. We're going to be nice to ourselves. The unit circle is a really, really useful and a circle we're going to come back to a lot. It's a special circle with a radius of 1. Therefore, its circumference, the whole distance around the outside, is 2 pi, which also means that the arc is going to be equal to the angle, because, remember, arc length is equal to radius times the angle. The radius is 1, then the arc length is equal to the angle, which just makes everything so much nicer. So we can kind of see here that if I go all the way around, if I had the entire circle, which you would refer to previously as 360 degrees, that's now 2 pi radians, which means half of a whole circle, 180 degrees, is pi. Half of that, which is 90 degrees, is pi over 2. So we can use these fractions of pi to help us out. So if we're ever doing a conversion, I would always do the conversion that pi radians is equal to 180 degrees. Although I will say it would be so helpful for you, specifically to try to think just in terms of radians. If you're having to convert all the time, one, it's going to take a lot more time, and two, you might miss some connections and some really cool like aspects of the math if you're not thinking with radian sense. So because we're mapping now all of our angles onto a circle, essentially, anything past 2 pi radians, anything past 360 degrees, gets mapped into a place that was already mapped to from 0 to 2 pi. So what do I mean by this? I mean that 3 pi has the same terminal angle, has the same terminal like ray as pi radians. So we would call those two angles, 3 pi and pi, coterminal. So if I want to find a coterminal angle, we can use our idea of what the circle is to figure that out. So if I want to find an angle between 0 and 2 pi that is coterminal with 4.3 pi, well, how many times to go around the circle? I went around the circle, 2 pi is 1, 2 pi again would be again. So essentially what I need to do is if it's larger than 2 pi, I need to take 2 pi away from it until I get between 0 and 2 pi. And if it's less than 0, I need to add 2 pi to it. Remember, we can deal with negative angles. It just means that we went clockwise instead of counterclockwise. So what I'm going to do is I'm going to subtract 2 pi until I get a result that is within 0 to 2 pi, and I get 0.3 pi. So 3/10 of pi would have the same terminal ray as 4.3 pi. That's pretty cool. So that's all fine and dandy. We've been talking about angles for a while now. The lesson's name is sine, cosine, and tangent. Well, let's finally add those to play. So if we recall from right triangle trigonometry, sine I know it's abbreviated SIN, remember it's sine, we don't sin in math class, is the opposite side of a right triangle divided by its hypotenuse. And remember, we always label what angle we're referencing here, and we're always going to make our reference angle standard position. So we're always going to draw a reference, we're always going to draw our triangles with one side on the x-axis. So that's why it kind of looks a little weirder with the way it looks right now. Cosine is adjacent over hypotenuse, tangent is opposite over adjacent. You may have remembered this as SOHCAHTOA. Whatever mnemonics you used, or whether you just outright memorized it, this is not information that is going away. You're going to have to know this for application problems, or maybe even some of the connections that we're going to make later. So this needs to be memorized. So remember that our angles are in standard position. How does the right triangle trig relate to that? Well, we can take our circle, and if we pick a point on our circle, we can always make a right triangle with it. So right here, we've picked a point in the quadrant 1, and you can see I can drop down an altitude for that point, and the coordinates of the point, coincidentally, if the radius is 1, this distance x would be the x-coordinate, and the vertical distance y would be the y-coordinate. Again, that works if the radius is 1. If the radius isn't 1, then those values would differ slightly. And the radius is always going to be the distance from 0, 0 to the point itself. So that's great, fine and dandy. How does it work if the point's over here? So if I draw a point here, again, I can draw so it intersects the x-axis. Very important that it's the x-axis. And then I can draw the radius there, and I get a right triangle. And I know that this angle here is going to be pi radians, so this angle would be that much more. So we still get that same idea. We can turn any angle on the circle, or any point on the circle, into a right triangle. And therefore we can find the sine, which would be the vertical distance divided by the true distance, the cosine, which is the horizontal distance, divided by the true distance, and then the tangent, which is the vertical distance divided by the horizontal distance. Same idea that came from those right triangle trig definitions that we just talked about. Something cool is that if I do a little bit of algebra magic, if I take this y over x, right, and I multiply both of them by r, remember multiplying by something over itself is 1, do some rearranging, I get sine times 1 over cosine. So tangent is equivalent to sine divided by cosine, and that's going to be very important a lot later. So, given this angle here, and I don't know much about the angle, right? I know that it's somewhere between pi over 2 radians and pi radians, but I don't really know anything. Let's find the sine, cosine, and tangent values. So if you noticed from all of these, the one thing that we're really missing is the radius. And the cool thing is again, since we can turn all of these into right triangles, essentially, we know that this is -3, this is 1, so we can find the hypotenuse of the triangle, and that's the radius. So we're going to do 1 squared plus -3 squared is equal to r squared. Or if you know the distance formula, which is just a modification of the Pythagorean theorem, you could always say that r is equal to the square root of 1 squared plus -3 squared. 1 squared is 1, -3 squared is 9, 9 plus 1 is 10, so the radius is the square root of 10. So now we have all of our stuff that we need. Sine is y divided by r. So y is 1 divided by r is the square root of 10. And here's where we're going to start rationalizing our denominator. Quite often we're going to get square roots in the denominator in some of these, and we can't leave square roots in the denominator. We have to make sure that our answer only has an integer in the denominator. So what we're going to do is we're going to multiply the numerator and denominator by the square root of 10 over the square root of 10, which gives us the square root of 10 over 10 to be our final answer for sine there. Cosine, we're going to end up with something similar. We have -3 over the square root of 10. If you've picked up on what the trick leads to and to what our simplification leads to, you can automatically go there, -3 root 10 over 10. And that's perfectly fine. Tangent, super easy. It's the y divided by the x. And you can leave the negative in the denominator. I like pulling it out and having negative 1/3 being our final answer there. And that's it really. Not much more. This one's cool because not only did it give us the point x, y, but it also gave us essentially the radius. It's telling us from 0, 0 to this point, it's 6, 0. That radius has to be 6. So the radius is 6, and we don't have to do Pythagorean theorem for it. Hallelujah. And it's also not a root, so it makes life even better. So sine is y divided by r. So that would be negative 5.4 divided by 6. We can reduce this, but for our intents and purposes, we have an integer in the denominator. I think it's fine. Cosine, we have x over r, which is 2.6 divided by 6. And then finally, tangent is y divided by x, which would be negative 5.4 over 2.6. And is that nice? I think that is actually 5.4 divided by 2.6. No, it's not. No. So leave it like that. All right. Why use the unit circle? So we talked about the unit circle before and it went away. Why use the unit circle? Why talk about it? Well, instead of sine being y over r and cosine being x over r, if we're dealing with the unit circle, the radius is 1, it simply means that the y-coordinate is sine and the x-coordinate is cosine. And that makes life even better. So if we look here, we have a unit circle. The radius of the circle is 1. And we have a point negative 0.65 and negative 0.76. Much easier to actually find this information because the sine is the y, which is negative 0.76. The cosine is the x, which is negative 0.65. And tangent is still y over x. It doesn't really get simplified, but it's the same, so that's always nice. To negative 0.76 divided by negative 0.65. Negatives would cancel. That would leave us with, I'm going to go with 65/, mainly because I like to have integers in my denominator. And that is it for this lesson. If you have any questions, please make sure you ask. Otherwise, I'll see you in the next lesson.